Hello all, welcome to this video on operating systems. The topics we'll be dealing with today are mutex locks and semaphore usage and implementation. Let's begin. The hardware-based solutions to the critical section problem that we discussed in the previous video are complicated as well as generally inaccessible to application programmers. Instead, operating system designers build software tools to solve critical section problem. The simplest of these tools is a mutex lock. In fact, the term mutex is the short for mutual exclusion. We use the mutex lock to protect critical regions and thus prevent race conditions. That is, a process must acquire the lock before entering a critical section and it releases the lock when it exits the critical section. The acquire function acquires the lock. The release function releases the lock. And this is illustrated here. A mutex lock has a Boolean variable called available whose value indicates if lock is available or not. If a lock is available, then a call to the acquire function succeeds and the lock is considered unavailable. A process that attempts to acquire an unavailable lock is blocked until the lock is released. This is the definition for acquire. Here it is clear that the while loop executes based on the value of available. If the value of available is false, it means that this lock has been already acquired by some other process. Hence, this process will go into a busy wait state. When the other process releases the lock, it will set that available value to true. Hence, this while loop will break and this process will set available value to false and acquire the lock. And this is the definition for release. In release, the acquired lock is released by setting the value of available as true. Calls to either acquire or release must be performed atomically. Thus, mutex locks are often implemented using one of the hardware mechanisms we discussed in the previous video, that is either test and set or compare and swap. The main disadvantage of the implementation given here is that it requires busy waiting. While a process is in its critical section, any other process that tries to enter its critical section must loop continuously in the call to acquire. In fact, this type of a mutex lock is called a spin lock because the process spins while waiting for the lock to become available. This continual looping is clearly a problem in a real multi-programming system where a single CPU is shared among many processes. Busy waiting wastes the CPU cycles that some other process might be able to use productively. Spin locks do have an advantage, however, in that no context switch is required when a process must wait on a lock, and a context switch may take considerable time. Thus, when locks are expected to be held for short times, spin locks are useful. They are often employed on multiprocessor systems where one thread can spin on one processor while another thread performs its critical section on another processor. Now let's look into semaphores. Mutex locks are generally considered the simplest of synchronization tools. Here we are going to see a more robust tool that can behave similarly to a mutex lock but also provide some more sophisticated ways for processes to synchronize their activities. That is a semaphore. A semaphore S is an integer variable that, apart from initialization, is accessed only through two standard atomic operations: wait and signal. The wait operation is originally termed P from the Dutch word proberen, which means to test. Signal originally is called V from verhogen, which means to increment. The definition of wait is given here. So whenever the value of S is less than or equal to 0, this loop goes into a busy wait. In other cases, the value of S will be decremented by 1, and in case of signal, the value of S will be incremented by 1. All modifications to the integer value of the semaphore in the wait and signal operations must be performed indivisibly. That is, when one process modifies the semaphore value, no other process can simultaneously modify that same semaphore value. In addition, in the case of wait of S, the testing of the integer value of S, that is S less than or equal to 0, as well as its possible modification S minus minus, must be executed without interruption. Next, we'll move on to a semaphore usage. Operating systems often distinguish between counting and binary semaphores. A counting semaphore value can range over an unrestricted domain. The value of a binary semaphore can range only between 0 and 1. Thus, binary semaphores behave similar to mutex locks. In fact, on systems that do not provide mutex locks, binary semaphores can be used instead for providing mutual exclusion. Counting semaphores can be used to control access to a given resource consisting of a finite number of instances. The semaphore is initialized to the number of resources available. Each process that wishes to use a resource perform a wait operation on the semaphore, decrementing the count. When the process releases the resource, it performs a signal operation, incrementing the count. When the count for the semaphore goes to 0, all the resources are being used. After that, processes that wish to use a resource will block until the count becomes greater than 0. We can also use semaphores to solve various synchronization problems. For example, consider two concurrently running processes, P1 with a statement S1 and P2 with a statement S2. Suppose we require that S2 be executed only after S1 has completed. We can implement this scheme readily by letting P1 and P2 share a common semaphore sync initialized to 0. In process P1, we insert the statements S1, signal of sync, and in process P2, we insert the statements wait of sync S2. Because sync is initialized to 0, P2 will execute S2 only after P1 has invoked signal of sync, which is after S1 has been executed. Now we will move on to semaphore implementation. Recall that the implementation of mutex locks suffered from busy waiting. Here also the definitions for wait and signal semaphore operations have the same problem. To overcome the need for busy waiting, we need to modify the definition of wait and signal operations as follows. When a process executes wait operation and finds that the semaphore value is not positive, it must wait. However, rather than busy waiting, the process can block itself. The block operation places the process into a waiting queue and switch it into waiting state. Then control is transferred to the CPU scheduler, which selects another process to execute. A process that is blocked waiting on a semaphore S should be restarted when some other process executes a signal operation. the process is restarted by wake up operation, which changes the process from waiting to ready state and place it in the ready queue. To implement semaphores using this definition, we define the semaphore as given here. Each semaphore has an integer value and a list of processes list. When a process must wait on a semaphore, it is added to the list of processes. A signal operation removes one process from the list of waiting processes and awakens that process. Now, wait semaphore operation can be defined as follows. Here the value of S will be decremented by 1. Whenever its value is less than 0, it will be added to the process list and the process is sent to a blocked state. And this signal semaphore definition is given here. Here the value of S is incremented, and if its value is less than or equal to 0, then it is removed from the process list and the process is restarted using wake up. Block operation suspends the process that invokes it, and the wake up operation resumes the execution of a blocked process. These two operations are provided by the operating system as basic system calls. Note that in this implementation, semaphore values may be negative, whereas semaphore values were never negative under classical definition of semaphores with busy waiting. If a semaphore value is negative, its magnitude is the number of processes waiting on that semaphore. This fact results from switching the order of the decrement and the test in the implementation of wait operation. The list of waiting processes can be easily implemented by a link field in each PCB or process control block. Each semaphore contains an integer value and a pointer to the list of PCBs. One way to add and remove processes from the list so as to ensure bounded waiting is to use a FIFO queue, where the semaphore contains both head and tail pointers to the queue. In general, however, the list can use any queuing strategy. Correct usage of semaphores does not depend on a particular queuing strategy for the semaphore lists. It is critical that semaphore operations be executed atomically. We must guarantee that no two processes can execute wait and signal operations on the same semaphore at the same time. This is a critical section problem, and in a single processor environment, we can solve it by simply inhibiting interrupts during the time the wait and signal operations are executing. This scheme works in a single processor environment because once interrupts are inhibited, instructions from different processes cannot be interleaved. Only the currently running process executes until interrupts are re-enabled and the scheduler can regain control. In a multiprocessor environment, interrupts must be disabled on every processor. Otherwise, instructions from other processes may be interleaved in some arbitrary way. Disabling interrupts on every processor can be a difficult task and furthermore can seriously diminish performance. Therefore, symmetric multiprocessing systems must provide alternative locking techniques such as compare and swap or spin locks to ensure that wait and signal are performed atomically. It is important to admit that we have not completely eliminated busy waiting with this definition of wait and signal operations. Rather, we have moved the busy waiting from the entry section to the critical section of application programs. Furthermore, we have limited busy waiting to the critical sections of the wait and signal operations, and these sections are short. That is, if properly coded, they cannot be more than 10 instructions. Thus, critical section is almost never occupied and busy waiting occurs rarely, and then for only a short time. An entirely different situation exists with application programs whose critical section may be long, like for minutes or even hours, or may almost always be occupied. In that case, busy waiting is extremely inefficient. That's all for now. Thank you. Thank you for listening.